Of course.
Okay, so if you need to stay after tonight, again, I'm available if you want to just make something up or get a little extra help before the midterm. Your lab report is due next week, okay, the next time you see me. Please get it to me, at least just drop it in my box before Wednesday. I need to have grades in by Friday. So let's talk about Lewis structures. For the test, for the midterm, you're gonna have to do some simple Lewis structures. So what would I put in the center? For carbon tetrachloride, what would I put in the center? The chlorine or the carbon?
Carbon.
I put the carbon in the center because, why? Because it's the least electronegative. It's the least electronegative. The terminal atoms are going to be the chlorines. So I'm just going to make some single bonds to chlorine. Let me do this slower, sorry. So let me make some single bonds to chlorine to start off with. That's all I need to do, just some single bonds. Is that okay so far? And now, after that, I'm going to put electrons on the terminal atoms until I fulfill the octet rule. So I'm just going to put electrons on the chlorines until they fulfill the octet rule, meaning that they have 8 electrons around them total. You're going to have to imagine those 2 at the top there, sorry. Okay? So now you can see each of these chlorines obeys the octet rule. Does the carbon obey the octet rule? It does. Let's count up the total electrons we should have in this molecule and make sure we've accounted for them all. Okay, so chlorine has 7 electrons total, and there are 4 of them, so that's 28 total electrons, plus the 4 from carbon. Carbon has 4 electrons, right, in its valence because it's in group 14. So I should have a total of 32 electrons. That's how many I should have, so let's count them up. You ready? 2, 4, 6, 8, 10, 12, 14, 16 at the top, 18, 20, 22, 24, 26, 28, 30, 32. So this is a good structure. I've used all the electrons. Is there any formal charge? Are there any pluses or minuses in it? Nope. And one of my jobs is to minimize formal charge. So this is a great structure. This is a very stable molecule. Now all I have to do is determine whether or not it's polar and its shape. The shape is going to determine whether or not it's polar. So you're going to use this reference on the back of your study guide for determining shape. All right, and all we do to determine the shape is just think about how many things are attached to the central atom. So this is the central atom, carbon. Right here, that's the central atom. Think about how many things are attached to it and tell me what the shape is. What do you think? What is it? Tetrahedron, right? Nice. Okay, so this is a tetrahedron. There's no lone pairs. There are 4 things attached to the central atom. So this is called a tetrahedron. Okay, for polarity, all you have to do is think about electronegativity. Which one's more electronegative, chlorine or carbon? Chlorine. So the electrons are being pulled towards the chlorine here, towards this chlorine, towards this chlorine, and towards that chlorine. They're being pulled in all directions. Is there one side of this molecule you could point to and say, there's a lot of electrons over here and not a lot over here? No. It's kind of being pulled in all directions equally. So is it polar or is it non-polar?
Polar.
It's non-polar. It's non-polar. What makes it polar is an unequal distribution of electrons. So let's say this was the case. What if I were to take these chlorines off and make them hydrogens? See how that changes these arrows? Now all of a sudden the carbon is pulling the electrons this way. Oops, sorry, I just broke my stylus. Now all of a sudden the hydrogen's electrons are being pulled towards the carbon this way. Now is there a side of this molecule that has an overabundance of electrons? Now this side over here has a lot of electrons, so it's partially negative. And this side over here has a lack of electrons, so it's partially positive. That sign that I just wrote, that's a lowercase delta. It's a Greek letter. We use it to indicate a partial charge. All right, so these electrons are being shared, but not equally. In this case, you could say this side is negative, this side is partially positive. So this is called a dipole. It's called a dipole, right? If you have a dipole, if there's a side that's negative and a side that's positive, it is a polar molecule. The word dipole and polar mean the same thing. All right, so this is polar. This molecule is polar. However, if I put those chlorines back in place, because all of those electrons are pulling in different directions, opposite directions, there's really no overall direction for polarity, right? So this molecule right here with the chlorines in place, that is nonpolar. All right, so this molecule right here, this is nonpolar. All right, so if it's nonpolar, and you put two of them together in the same space, would they stick to each other? No, they wouldn't stick. There's not really much force of attraction. We call that intermolecular force, where they're neither of them are polar. They're not going to stick very well together. What do we call that?
Dipole.
Dispersion forces. Dispersion. All right? So this is a tetrahedron. It's nonpolar, and therefore, there's no real good force of attraction between these molecules. It's just dispersion. So would you expect this to be a solid at room temperature?
No.
Wouldn't be. It would not be a solid. Solid at room temperature has to be held together by very strong intermolecular forces, namely an ion attracted to another ion, right? That's a very strong force of attraction. It would be a solid at room temperature. Think table salt, right? NaCl. Two ions connected, they form a solid at room temp. Okay, what about sulfur dioxide? Let's do that one. So what would I put in the center for sulfur dioxide? Put the sulfur in there. And then I just make some single bonds to oxygen like that. Okay? Now I put electrons on the terminal atoms until they obey the octet rule. So 2, 4, 6, and then 8. Right? That obeys the octet rule. 2, 4, 6, and this is 8. So now the oxygens obey the octet rule. Does the sulfur? It doesn't. So in order to fix this problem, I'm going to take some of the electrons off the oxygen. And here's another reason why I'm going to do that. And this one's really important. What's the formal charge on this oxygen right now? What's the formal charge right here? It's negative, exactly. Here's why. Okay, if you don't know that, this is how we count them up. Oxygen in this scenario owns 1, 2, 3, 4, 5, 6, and 7 electrons. That owns 7 electrons. How many does it normally own? 6, because it's in group 16. So with one additional electron, it has a formal charge on it of 1 minus, okay? What about this oxygen over here? Same thing?
Yeah.
Same thing. So we've got 2 minus charges on this thing, and remember, one of your goals for making a structure that's stable is to minimize the formal charge. So in order to do that, I'm going to take 2 of these electrons off, and I'm going to move them into a double bonding position. That's going to get rid of the charge, and it's going to help to fulfill sulfur's octet rule. So remember, you start by putting the electrons on the outermost atoms. If they're negative, make a double bond. All right? So now the structure is going to look like this. Sulfur in the center, double bonded to oxygen. And these 2 oxygens are just going to have 2 lone pairs instead of 3. What's the formal charge on those oxygens now? How many electrons do they own? 6. 6. And here, let me count them up for you. All right. 1, 2, 3, 4, 5, and 6. They own 6. All right, so that's neutral. So no formal charge. Does sulfur now obey the octet rule?
Yes.
It does. Ah, that was not what I had in mind. Dear God in heaven. All right, let's try again. Okay, so here's the trick. At the very end, this looks good to me so far, right? So if you were just doing this without counting up all the electrons you needed, you might think you're done. How many electrons do I really need though? Let's count them up. 2 oxygens. How many electrons does oxygen have to start off with?
6.
6, so that's 12 total, right? Plus another 6 for sulfur. I'm going to add that in. So how many electrons am I looking for? 18 total. Let's count them up. Ready? 2, 4, 6, 8, 10, 12, 14, 16, 18. Ah, thank you. Sorry. She's right. That's extra. Okay? So this is the structure I'm supposed to draw. And that has 16 electrons. So I'm shy by 2. Now here's the question. If the oxygens obey the octet rule right now and there's no formal charge in this molecule, where should I put this extra pair of electrons? On the sulfur. And here's why. Because sulfur, if you don't have this on your periodic table, write it in now. Starting with phosphorus at 15, phosphorus, sulfur, and chlorine, and everything below those can expand the octet. They can make more than the normal 4 bonds. So it's normal to see sulfur like this. In this case, sulfur has, if you count them up, sulfur has 2, 4, 6, 8, 10 electrons around it. And that's okay for sulfur. It can expand the octet. Do you want to know why it can expand the octet? Do you want me to go back through that?
Yeah.
Do you care? Okay, let me show you real quick. So sulfur's electron configuration, you will need to know how to do this for the test. Sulfur's electron configuration, it has 16 electrons total. What noble gas do I put right here in brackets? The one before, right? So neon goes in brackets. And then I start with 3 because I'm in the 3rd period. After neon, I'm in 3, the 3rd principal quantum number. Then I have to go through the S block. I have to go through sodium and magnesium. So that's 3s2, that's full. And then I have to go through the P block to get to phosphorus, right? So it's going to be 3p, careful, 3p. How many into the P block are you? Aluminum, silicon, phosphorus. 3. So it's 3p3. Looks like this. Okay? So that's the electron configuration right now. Here's the trick. When you get to sulfur, it's so big that the bands, the energy gap between the orbits is very small. Remember, as you move away, the orbits get closer and closer together in energy. They're very close in energy here. So that 3D is sitting right here very close in energy with empty orbits. And this electron can jump into that orbit. It's not a big jump. And now it can make an additional bond. And bonding is really favorable. Making more bonds is always better, more stable. Make sense? So in order to make this little jump, it doesn't have to use a lot of energy, but it can make an additional bond, and that's really favorable. This little jump right here, jumping an electron from here to there, that might take about 20 kilojoules per mole. Making an additional bond, however, can earn this thing about 200 kilojoules per mole. So it's a huge difference in energy and stability if you can make that additional bond. Does that make any sense? Yeah. It's just because the d orbit is so close in energy, electrons can make the jump and make an additional bond. All right, so this structure here, let's determine what shape that is. All right, so look at that structure. Look at your Vesper chart. How many things are attached to this central atom? Careful. How many total things that take up space are attached to the central atom? 3 because of that lone pair. Don't forget about this lone pair. All right? So what's the shape? It would be, except this is a lone pair, so it's bent. All right. That changes everything. If it was linear like I've drawn it, it would look, the polarity would be non-existent because there's a pole this way and it's equal and opposite from this way, right? The oxygens would be pulling the electrons towards opposite poles, so you couldn't say this side's more negative than that side. You couldn't say that because it's equal in both directions, right? So that would be nonpolar. That's not what it looks like. It looks like this: sulfur and oxygen, and it's bent. So now the pull is down this way and down that way, and now you can say for a certainty, this side over here, that's partially positive. This side over here, partially negative. There's an accumulation of electrons at the bottom of this thing, so now there's a pole on each side. That's called a dipole. If it has 2 poles, if it has a positive side and a negative side, it's called a dipole. Remember, this is not an ion. It's just partial charge. This is a sharing of electrons. It's just kind of unequal because the oxygen is so much more electronegative than the sulfur. So if you put 2 of these molecules in the same space, like this, so this is a very similar molecule. They're bent, right? This is water. Water. Test. Water's gonna, yeah, okay. If you put 2 waters next to each other, they're gonna line up like this. Why? Why not like this? Exactly. The hydrogens are positive and they'll repel each other. They'll line up automatically like that. Positive and negative attracted to each other. That's the electromagnetic force. That's the force we're dealing with in chemistry. Okay? So this is a bent molecule and it's polar. For a certainty, it's polar. What force of attraction is going to be holding it together? Dipole-dipole interaction. Fairly strong, right? You'd expect it to either be maybe a liquid at room temperature, something like that. Maybe a volatile liquid, but you might expect it to be a liquid at room temperature. Is this okay? Okay. Let's try. Let's just do dinitride just to finish off, okay? So if I had, how many, what's in that dinitride? 2 nitrogens, yeah. How many bonds does nitrogen tend to make? It's in group 15. How many bonds does it need to make to look like neon? 3. Look at its oxidation state. What's its oxidation state? That tells you how many electrons it needs to gain in order to look like neon, right? So it's going to make 3 bonds. So I'm just going to make 3 bonds between the 2 nitrogens. Does that obey the octet rule?
No.
No. So I'm going to put 2 more electrons on the nitrogens like that. Why didn't I just make another bond? You can't. 3 bonds, a triple bond, is the maximum number of bonds you can make between 2 atoms. The rest have to be lone pairs. So now they both obey the octet rule. Let's make sure we use all the electrons. How many electrons does nitrogen come with?
5.
Comes with 5 times 2, right? There's 2 of them, so that should be 10 total. Let's count them up. 2, 4, 6, 8, 10. No formal charges, right? No formal charges. That's a good start. So this is the type of thing you'll be expected to do for the test. Is this linear? What happens when you connect 2 points on a graph? It's a line. So this is linear. Is it polar? Is it polar? It's not polar. Here's why. What's the difference in electronegativities? It's 0. This is a non-metal bonded to a non-metal, right? It's going to make a covalent bond. And in this case, there's no difference in electronegativity, so it's not polar. There's no tug on the electrons in one direction or the other. Linear, non-polar, what would be the force holding these things together?
Dispersion.
Dispersion only, and that's a weak force. So would you expect this to be a gas, a liquid, or a solid at room temp?
Yes.
A gas, exactly. breathing it right now. Okay? Making sense? Okay. Try one on your own before you leave the room, okay? And remember them after tonight if you need extra help.